In this video, I want to talk about first order circuits. So before I do that, let's just quickly go over the equations that we had for the inductors and capacitors. So if you remember from before, I said that the voltage in an inductor is the result of multiplying the size of the inductor, which is measured in Henry, by the derivative of its current over time. So based on this equation, and by doing some calculations, you can see that the current at any given time is 1 over L, the integral of the voltage from time equals t0 to any time, plus the initial current of the inductor. Combining these two, we can get the equation for the power, and then by taking the integral of this equation over time, we can get the equation for energy, which is 1 over 2 Li squared. As for the capacitors, the current that goes through the capacitor at any given time equals the size of the capacitor multiplied by the derivative of the voltage across it over time. And then by doing some manipulations, the voltage across the capacitor at any given time equals 1 over C, the integral of the current that goes through the capacitor from time t0 to any time t, plus the initial voltage of the capacitor. Again, by combining the two, we can get the equation for the power, and by taking the integral of this equation, we can get the equation for the energy, which is 1 over 2 CV squared. So inductors and capacitors, unlike the resistors, which had a very simple relationship for the voltage and current, which was V equals Ri, they require taking derivatives. So for the inductor, the voltage is proportionally related to the derivative of the current over time, and for the capacitor, the current is proportionally related to the derivative of the voltage over time. We also talked about how we can connect inductors and capacitors in series and parallel too. So inductors, they behaved similarly to resistors. So if you had a bunch of inductors connected in series, the equivalent inductance was the result of summing all the inductors that were connected in series. And when they were connected in parallel, 1 over the equivalent inductance was the summation of 1 over L1 plus 1 over L2 plus all the way to 1 over Ln. Whenever we want to connect inductors in series, we have to make sure that the initial currents of the inductors are exactly the same for all of them. Because based on this equation, we cannot have a sudden change in the current of the inductor, because that means that we need to have an infinite amount of voltage. When we were connecting inductors in parallel, we didn't have that requirement, but the initial current of the combination of the inductors was calculated by summing all the initial currents of the individual inductors that are connected in parallel. So in effect, inductors can store energy in a form of current. Capacitors, on the other hand, behaved similarly to conductance components. So if you remember, conductance was the reciprocal of the resistance. So if you have some capacitors connected in series, 1 over the equivalent capacitance was 1 over C1 plus 1 over C2 all the way to 1 over Cn. And for the voltage across the equivalent capacitance, it was as a result of summing all the voltages of the individual capacitors that are connected in series. On the other hand, when they were connected in parallel, the equivalent capacitance was equal to the sum of all the individual capacitors. When you connect capacitors in parallel, you need to make sure that they all have the exact same initial voltage, because as you can see, current is related to the derivative of the voltage, so we cannot have sudden jumps in the voltage because that requires having infinite amount of current, which is physically impossible. So capacitors store energy in the form of voltage. So now that we went over this summary, we need to know what happens if we connect inductors and capacitors into resistive circuit. So how does connecting capacitors and inductors affect the voltages and currents that we may have in the circuit? So here we only focus on circuits that contain some sources, resistors, and only one inductor or capacitor. And by only one, you can also consider if you have several of them connected in series or parallel, that they can be reduced to a single equivalent inductor or capacitor. So such circuits are called first order RL or resistor inductor, or RC resistor capacitor circuits. So there are three different types of responses that you can get from these type of circuits: natural, step, and the general solution. So the natural step is the result of analysis of a circuit when the stored energy in an inductor or capacitor is suddenly released in an all resistive circuit. So for this case, we don't have any source, we only have an inductor or capacitor with initial energy that is being connected to a circuit that is all resistors. For the step response, that is going to be the result of analysis of a circuit when energy is being acquired by an inductor or capacitor due to sudden application of a DC voltage or current source. So here, in addition to the resistor, what we have is we have a source as well. But this time we don't have any initial voltage for the capacitor or any initial current for the inductor. We just want to know how the capacitor or inductor would acquire their initial voltages or currents, or how they acquire energy. And then finally we can have the general response, which is a combination of the two. So we have both the natural response and a step response combined to create the general response. As you see on the right, we can have several configurations. So one thing that you might notice here is that I considered the inductor or the capacitor to be connected between these two nodes, and then they are connected to VTH or RTH, or a combination of the two. So this is, you can say, the Thevenin equivalent circuit of the circuit that is connected between these two nodes. This one is the Norton equivalent. The same is true for these two circuits as well. So what we basically do is that we can also consider that these are equivalent inductance or equivalent capacitance, right? So what we basically do is that we consider them capacitors or inductors. We calculate the Thevenin or Norton equivalent circuit that are connected between their two terminals, and also, if needed, we calculate their equivalent inductance and capacitance too. So what we learned in this video was some introduction into first order circuit. We went over the definitions of natural response, step response, and general response. In the upcoming videos, I'm gonna go into much more details about how we can derive these responses by solving first order differential equations.